Okay, right. Am I audible to you?
Yes, sir.
Okay, my screen is also visible, right?
Yes, sir. Visible, sir.
Okay, right. Okay, we'll start the class now. So, in the previous class, we discussed about beam strength of a gear tooth. So, today we'll continue that. So, with the further again after that we'll see what is the wear strength of the tooth also, because these gears failures are majorly either due to strength failure or due to wear failure. So therefore, first we have seen beam strength. Then how we can use beam strength to identify that whether the gear tooth is going to fail or not based on this beam strength. After that, we'll discuss about the wear strength, and also we'll check according to wear strength when the tooth is going to be failed. So with that, we cover that analysis of this gear tooth. After that, we'll take some numerical examples. Okay, right. So in the last class, we already discussed about the beam strength, and we derived an equation for beam strength with some assumptions. So while calculating this beam strength, the most important point is, or important assumption is, effect of radial load is ignored. So PR is not considered, only PD is considered, and also this PD is assumed to be distributed throughout the length, width of the gear teeth, and stress concentration is ignored, as well as on more assumption is only one pair of teeth will take the total load. So with those assumptions, we derive an expression for the beam strength, which is in terms of PT. So then the maximum value of PT corresponding to the maximum tangential force, we call it as a beam strength. So that is the definition here. You can see the beam strength is the maximum value of tangential force. Tangential force, where PT is nothing but the tangential force. The beam strength is nothing but the maximum value of tangential force that the tooth can transmit without bending failure. We consider only bending failure. So we ignore the radial load, means we ignore the effect of compressive stress also. So therefore, from this we read, and this is the equation for the beam strength of a gear tooth. So SB is nothing but the beam strength, M is module, B is face width, sigma B is the allowable bending stress, and Y is called Lewis form factor. Y is called Lewis form factor. So now if I want to design the gear based on static load, so only beam strength is a static load. We are not yet to consider the dynamic load. So we'll come to that part later, how we can convert the static load into dynamic load. So here this is the equation only based on the static load. So this is, if you design the gear based on this equation, we'll call it as a gear design based on static load. So in this, like I said, M is module and B is the phase width, sigma B is the allowable stress, and sigma Y is sorry, not sigma Y, capital Y is Lewis form factor. So generally this Lewis form factor is will pick from the data book. Lewis form factor will be given in the data book. So depending upon the number of teeth, that is Z, and pressure angle phi or alpha. We are taking pressure angle is alpha, so we'll take it as alpha only. So number of teeth and alpha and type of teeth, whether it is full depth or subtooth, based on that we can pick this Y value. Okay, so once you got that, then you can find out the bending strength. So based on that, you can say that whether it is going to be fail or not. The beam is gear tooth is going to be fail or not based on this equation. So in this equation, again one more point here is the sigma B, the allowable bending stress in a gear teeth. Generally we'll take it as SUT divided by 3. Since these gears are made of cast iron or something like that, FG grade, so we'll use, instead of SYT, we need to use SUT. SUT divided by 3. So generally we'll consider a factor of safety of 3 for this to calculate this allowable stress. So this is a general rule. Suppose if he has given other than 3 in the problem, we'll take that value. If not mentioned, we'll take sigma B as SUT by 3. So with these points, we can easily identify that bending strength of a gear tooth. So now the next question is, okay, right. So here we derive the beam strength. Then in the gear drive, I have two gears. One is pinion, another one is the gear. Smaller one we'll call it as pinion, and larger one we'll call it as a gear. So out of these two, which one we need to consider to design, or which one we need to design first and which one we need to design next? That is the next question. So to answer that question here, we don't choose a proper. There is a proper way. There is a proper way of designing this gear train. So for that, what we need to is, out of these two, you need to pick which one is the weakest one or weaker one. It doesn't matter whether it is pinion or gear. So we don't bother. Either you are designing the pinion first and then gear next, or gear first or pinion next. But the criteria for that is, you have to identify out of these two, pinion and gear, you need to identify which one is the weaker. Then first will if you design for the weaker, means obviously the other one is going to be stronger. No need to design that. So if you design the weaker, stronger is if the weaker one is able to withstand the load, obviously the stronger one is also going to withstand the given load. So that means out of these two, no need to design both pinion and gear. Of course, once you know that, only thing is, in the design we are going to calculate only the module of the gear tooth. So module is going to be same for both pinion as well as gear. So that means if I design one, obviously I am going to design the other one also. But the only thing here is, what you need to do is, which one is the weaker one. Based on that only we need to decide how I can design, or how I can identify whether gear is weaker or pinion is weaker. So that depends upon again this equation. If you observe this equation here, let us assume that if both are made of same material, so both pinion and gear are made of same material. So in that case, this is going to be same. Sigma B is going to be same for both the materials. Sigma B is nothing but the allowable bending stress, which is going to be same. Then module is same. This one B, that is also same, because you have a specific relation between module and B. So when module of both gears are same, then only they can mesh it against each other. So if you have a one module and pinion, another module is on the gear, then you cannot mesh it. So therefore, what happens is, if the module is different, you cannot make it as a drive also. So therefore, module should be same. And also generally this beam, that is face width, is expressed as some constant times module. Always, let us say that constant is cm. We'll write it as, always this face width can be written as c sine to m. So where c is some constant, maybe let us say 10 times module or 5 times module or something like that. That means, so this b will also depend upon module. So therefore, since m and b are same for the both the gears, and sigma b is also same, then this beam strength will depend upon the factor only y. The factor y. So then y, in a previous class we derived what is the expression for y. So here the expression, if I go back, y is nothing but the Lewis form factor. So generally that form factor will be expressed, okay, I'll take it. So this one, t square by 2hm. So this is your y. So and also if you refer to some data books, they'll give the y factor as some constant value, let us say 0.5 minus some other value divided by number of teeth. So like that they'll give. So it is, this y is inversely proportional to the teeth. Y is going to be inversely proportional, directly proportional, because what happens here is, if t decreases, this x by t value will increase and y will decrease. If x by t increases, y will decrease. So that means t increases, y decreases. They are inversely proportional. So y and t are inversely proportional. So that means if number of teeth are more, y is going to be larger. If number of teeth are less, y is going to be smaller. So that means, so now from this what we can understand here is, so if you go back to this equation again here, since your ST is for a given material is depends upon, if you use same material for both gear and wear, gear and pinion, then SB will depends upon only Y. So that means the judgment is based on Y. So to identify which one is the weaker, you need to look at it into the Y value. So just now we said that this Y is inversely proportional to the number of teeth. So therefore, smaller one will have a smaller number of teeth and larger one will have larger number of teeth. So pinion is going to be the smaller one compared to the gear. So pinion is going to be the weakest one or weaker one. So if you use same material for both pinion and gear, then it is the pinion is going to be the weaker one. So that means your design should be based on the pinion. So this is the condition when you need to follow this one. You need to follow this condition when both gear and pinion are made of same material. So that is sigma B is also same. So that means we eliminated these three factors. Only SB is decided based on Y. Suppose if gear and pinion are made of two different materials, not the same material. If gear and pinion made of two different materials, then how we can decide which one is going to be the weaker? That is the next question. So now, even with that also, if the gear and pinion made of two different materials, so in that case, again I'll take this SB equation. So in this, I'll remove this one. So then your SB is proportional to, because for both the gear and pinion, M and B should be same. So therefore, these two are not going to influence, or these two factors will not decide which one is the stronger, which one is the weaker. Only this one, this SB is proportional to sigma B into Y. So that means, so you need to calculate the product of the allowable bending stress and Lewis form factor. Then out of these two, so that means you need to calculate SB sigma B into Y for pinion, as well as you need to calculate sigma B into Y for gear. So for both, you need to calculate this. Then which one is going to be the higher, that is going to be the stronger, or which one is going to be the lower? The sigma B into Y value is, let us say, if it is less for gear, then gear is the weaker. Or sigma B into Y of the pinion, let us say, I'll write like this, sigma B into Y. So this is the value I calculated for the pinion. If I use suffix P, that is for the pinion. Then sigma B into Y, I calculated this value for gear also. So then let us say, suppose if sigma B into Y of P is less than sigma B into Y by Z, then this is going to be weaker. Or else if it is something like this, if this value is larger than this value, this is going to be the weaker. So then your design is based on gear, not on the pinion. So like that, you need to decide. So if both gear and pinion made of same material, obviously pinion is going to be the weakest one or weaker one. So then the design is based on only pinion. If both are made of, both pinion and gear made of two different materials, then you need to calculate sigma B into Y for both pinion and gear. Then the value of the lesser value, which is having the lesser value, that is sigma B into Y is for which is less, that is whether for the gear or pinion, you need to take the lesser one and you need to design the gear based on that. So that means if it is less for gear, you have to take a gear as a design criteria. If it is less for sigma B into Y, this product is less for pinion, you have to consider pinion as the design criteria. Okay, so like that, based on the static strength or beam strength, we can design the gears. So that's what I think I have written here. The values of Lewis form factor are given in data book. Design of gear is required to decide the weaker between the pinion and gear. So that's what we already discussed. Now, always the design of gears are based on, first you need to pick the weaker one and then the design should be based on that weaker one only. So here, this is our Lewis equation or beam strength equation. We can call this equation as Lewis equation or beam strength equation is nothing but SB into MB sigma BY. It is observed that M and B are same for pinion as well as a gear. So like I already said, so why it should sway? If module is same, then only both the gears are able to mesh with each other. That is the law of gearing. Law of gearing. So from that your M should be same and always B is expressed as a some constant times the module. So therefore B and M are going to be same for both pinion as well as a gear. Then when different materials are used, the product of sigma B into Y decides the weaker between the pinion and gear. So the product of the sigma B into Y will decide the which one is the weaker one. The Lewis form factor is always less for pinion compared with gear. Why it is less? I said earlier. So Y is proportional to your number of, inversely proportional to the number of teeth. So teeth is more. Y is teeth is more. What happens? Y is going to be more. Like that you need to take. Y is proportional, not inversely proportional. So it is proportional. So then, therefore, always pinion is going to be the having less Y factor or Lewis form factor. So therefore, then if you use same material, when the same material is used for pinion and gear, the pinion always weaker than the gear, because if the same material means the sigma B will goes out of the equation, only Y is going to be the factor which will decide which one is the weaker. So then, since Y is always less for a pinion, so always your design should be based on pinion, not the gear. If not, they are not made of same material, then you need to take the product of sigma B into Y, and then which one is having the lesser value of sigma B into Y. So based on that, you need to design the gear, design the gear drive. So right, so that is the procedure. Okay, right. So now, how we can design that? So okay, I decided gear is the or pinion is the weakest one in those two things. So how I can design? Here we calculated only the beam strength. So I know this beam strength. I know this is the weakest one. Pinion is weakest one. I decided that also. Now how I can design that? So that means how I can find these values. What is the value of M? What is the value of B? Design is nothing but finding out the module. So now how I can find the module? So for that here, so our failure criteria is, okay, anyway, so this is the torque transmitted by the gear tooth, MT. So this is the repetition only. So we know that only the tangential component acts at the pitch circle radius. Therefore, MT is given as, or else PT is given by 2MD D dash, where D dash is the pitch circle diameter. The value of the tangential component depends upon the rated power and rated speed. We already seen this one also. In practical applications, here the torque developed by the source of the power varies during the work cycle. Similarly, the torque required by the driven machine also varies. So here always this torque, whatever MT is there, it is going to vary from the source as well as from the sink also. So that means where you are supplying the energy, there also it is fluctuating. Even where it is taking that energy, even that is also fluctuating. So that means both on driven and driven parts, this torque is going to vary. So that means, so if the torque is going to vary, what happened to your PT? Your PT also goes on varying. So it is not constant. But here what we are saying that the beam strength equation, we are calling it as a static load. The load is not varying. But in practical situation, this PT is not a static one, it is a dynamic one, because the torque is changing, this PT is also changing. So to account for this dynamic load, so there are two ways we can include this one. One is considering the velocity, pitch line velocity, or other one is proposed by the Buckingham dynamic load theory. So we'll see those things one by one now. So the two sides are balanced by means of, okay, so here this fluctuation is balanced by the flywheel. Okay, that is we're not going to concentrate on that one. In gear design, the maximum force is the criteria. So here, like I said, this PT is going to be fluctuate. So but our criteria, design criteria should be always we need to design for the maximum stress, and always we need to design for the weaker one. So now to calculate this maximum torque, a service factor need to be included into our equations. So therefore, the service factor CS is defined as maximum torque divided by the rated torque. So rated torque is nothing but the average torque, and maximum torque is maybe sometimes during the starting of a motor, the maximum torque is going to be maximum. So like that, we calculate based on the maximum torque and rated torque, we calculate the service factor. Now, if I take the service factor multiplied by this PT, then I get the dynamic load. So that's what, therefore, your service factor is nothing but MT max by MT, which is nothing but PT max by PT, where PT is the tangential force due to the torque. So now I'll get the maximum tangential force. So then rearranging this, so I can write maximum tangential force is nothing but service factor CS into PT. So now you can see that here in this table he has given depending upon the type of driven and driving gears, how the power is fluctuating on that. So we have a different service factors. So now here if we take working characteristic of a driving machine, so these are the column wise the characteristics of the driving machine, and on a row wise these are the characteristics of the driven machine. See, fluctuations are there on both driving machine as well as driven machine. If both are not fluctuating, that means both driving machine is uniform and driven machine is uniform also, in that your CS is going to be 1. So that means if there is no fluctuation, so then your PT max is going to be PT only. So then in that case, your service factor is going to be 1. Other than that, if anything, whether the driving machine has a fluctuation or the driven machine has a fluctuation, then your service factor is always more than 1. The minimum value is 1 and always it will more than 1. So then here if you have a light stock on the driving machine and on the driven machine it is uniform, still you have a service factor of 1.25. So similarly medium shock and a uniform on the driven machine it is 1.5. Like that, this table will give you the service factors for the different working characteristics of driving and driven machines. So based on this, we can pick the service factor and we can calculate PT max. So now once you have a PT max, with this PT max you can calculate the bending strength. So or else your bending strength, if it is bending strength is less than this PT max, then you can say it is design. It is safe, otherwise it is going to be fail. But before going to that, so it is not yet completed. This is whatever just by applying the service factor only, the load is not going to be the dynamic load. So we need to apply some more correction factors for this also. Okay, anyway, so for electric motors, so just now we derived or we defined service factor is nothing but maximum torque by rated torque. But in case of motors, generally the maximum torque is going to be the starting torque. So that maximum torque is replaced by starting torque in case of a electrical motors. So now, okay, like I said, when gears rotates at very low speed, almost at zero velocity, the transmitted load PT can be considered to the actual force present between the two machine gears. So that means if the speed of the gears is small or low, if the speed of the gears is low, then you can take whatever equation we got, PT max is equal to CS into service factor into your PT. This is PT max, the maximum value. But here the thing is, always gear trains are run at very high speeds, not on low speeds. Therefore, you need to consider some correction factor for this velocity also. So now if I want to introduce that correction factor, however, in most of the cases, the gears rotate at an appreciable speed and it becomes necessary to consider dynamic force resulting from impact between the mating teeth. So when the speed is high, so then during the machining there is an impact load on the teeth. So because two gears will come in fastly and they will come in contact with each other, that is nothing but a impact kind of load. So you need to consider a correction for that one also. So the dynamic force induced due to the following two factors. So why you need to apply this correction factor for this load in order to account for this high speeds? The reasons are maybe inaccuracies of the tooth profile. That means your invalid tooth profile is not properly cut, errors in tooth spacing, and misalignment between the bearings and elasticity of the parts. And finally, important thing is inertia of this rotating parts. So due to these things, you need to consider the dynamic load. So now to account for this, there are two methods. Like I said, there are two methods to account for this dynamic load. One is the approximate estimation by a velocity factor in preliminary stages of gear design, and precise calculation by Buckingham's equation in the final stage of design. So that means here you can account for this high speeds just by considering the velocity factor in the initial stage of design, and in the final stage of design you can go for the precise one, which is based on the Buckingham's equation. So we'll see what are the equations and what are the velocity factor also. So now it is difficult to calculate exact magnitude of the dynamic load in the preliminary stages of the gear design, because you never know how much, what is the speed and how much impact it is going to be taking place. So therefore the approximation method, that is to overcome this difficulty, the velocity factor is developed by Buck, and is going to be used to calculate the dynamic load. So that means beam strength is the static load, then we are converting to the dynamic load by multiplying the service factor as well as this velocity factor. So how you define this velocity factor? This velocity factor is depends upon the pitch line velocity of the gear. So for ordinary and commercially cut gears made with palm cutters and having V is up to 10 meter per second, where V is the pitch line velocity. V is less than 10 meter per second, then CV can be taken as 3 divided by 3 plus V. CV can be taken as 3 divided by 3 plus V, where V is the pitch line velocity. Suppose if V is more than 10 and for accurately arced and generated gears with V less than 20 meter per second, so more than 10 and less than 20, you can take like that. You can take CV as 6 divided by 6 plus V. Then for a precise gears with shaving, grinding and lapping operations and with V greater than 20 meters per second, CV is taken as 5.6 divided by 5.6 plus square root of V. So in this all these cases, V is the pitch line velocity, which should be expressed in meters. That is important thing. Always your V should be in meters per second, and the pitch line velocity is calculated using this formula. V is equal to pi d dash n by 60 into 10 cube, where d dash is nothing but the pitch circle diameter of the pinion or gear, based on which you are going to decide that is going to be the its corresponding pitch circle diameter, and n is its corresponding speed in RPM. So using that you can calculate the velocity. Once you calculate the pitch line velocity, then so whether it is less than 10 or between 10 to 20 or more than 20, you can choose the CV value using these conditions. So once you have CS and CV, finally you can write the effective load between the two machine gears as P active is nothing but CS P into PT divided by CV. Always the CV value is less than 1. So therefore you need to consider that in the denominator of this P active load. So that means, so using beam strength we calculated the static load. Then we introduce a service factor to account for the variable working characteristics of driven and driving gears. So that through CS, and then so because of high speeds, so in order to consider the effect of this high speeds, we introduce another parameter which is called velocity factor. So using CS and CV, now you can convert the total load or effectively you can calculate the effective load. So the effective load is going to be CS PT divided by CV. So therefore, using this P effective load, then only we can calculate or we can design the gear. So your P effective should be, for your design should be safe, your P effective should be less than, the effective load on the gear should be less than the beam strength of the gear. Then you can say that the gear is going to be safe. Otherwise, gear is going to be failure or you need to redesign your gear. Okay. I think I'm online or my connection is disconnected. Okay, it is fine, right? Hello?
Banon, sir.
Maybe just the power fluctuation is there. Okay, anyway, so it's not disconnected. Right, we'll continue. Right, so therefore, we are seeing how to calculate the P effective now. So your P effective should be effective load on the gear tooth should be less than its beam strength. Then that is the criteria for the design. Okay, so the elastic factor. Okay, so here the thing is there, even though we are considering the elastic factor, which is not, like I said in the beginning, it is an approximate way of identifying the load. So it is an empirical relation developed by the past experience, and it has some advantages as well as the disadvantages also. Okay, anyway, we are not going to focus much on this. The advantages are it is easy to calculate the velocity factor. Velocity factors have a sanction. So even AGMA, that is American Gear Manufacturing Association, also accepted this way of calculating the load. So that is another advantage. They are used in the past from many years and given the satisfactory results. Even though it is an approximate approach, it is giving satisfactory results. So therefore, you can follow that. So, but the disadvantage is the dynamic load depends upon number of factors such as mass of the gear, mass connected to the gear shaft, properties of the gear material like modulus of velocity. A good gear tooth of a material with low modulus of velocity will deflect more than the gear tooth of the material with having higher modulus. So we know that. So elasticity of modulus elasticity indicates the stiffness. Which one, if the stiffness more, deflection is less, and other things being equal, will absorb the energy and of impact and reduce the dynamic load. So this is the sum of the factors. Velocity factor method neglects these factors. It assumes that the dynamic load depends upon only the fixed line velocity. So these are the drawbacks of this method. So it is not considering the resilience of the gear material. So it is considered only the pitch line velocity. Based on that only, it will find the dynamic load. So the use of velocity factor is restricted to the limited range of pitch line velocities only. So here less than 10 and more than 10, between 10 to 20 and more than 10. Suppose if it is 50, there is no way. So you have to consider the same value. That means you don't have a velocity factors for a wide range of velocities. So that is the another limitation for this velocity factor. So, but even though we'll use the same thing. So if you use that, so you have to follow that approach. Or else, with those assumptions, you don't want to go for that one. If you want to go for the precise value for the dynamic load, that is given by this Buckingham. So in the final stage of gear design, where gear dimensions are known and errors are specified, and the quality of gears is determined, the dynamic load is calculated by the equations derived by this Buckingham. So in that case, the effective load. So here we consider, if you won't consider this bucking load, so if you want to consider the elastic factor, your effective load we write it as E effective as CS into PT divided by CV. So we said it is an approximate way of estimating the effective load. But if you want to have a precise one, instead of using this equation, you have to use this equation. P effective is equal to CS into PD plus PD. So PD is nothing but the dynamic load here. CS into PD is nothing but the load which comes from the tangential component of the force, and for that you need to add this dynamic load. So where PD is the dynamic load or additional load due to dynamic conditions between the two meshing teeth, and is given by, so Buckingham has given the equation to calculate this PD. So that is nothing but PD is equal to 21 into V into CEB plus PD divided by 21 into V plus square root of CEB plus PD. So no need to remember these formulas. These formulas are available in your data book. So you straight away you can use this PD equation. Only thing is you should know this one, but this equation is given in the data book. So no need to remember this. Okay, so that means instead of using the velocity factor, if I want to use the precise calculation of the dynamic load, I will go for this equation. So P effective is nothing but CS into PD plus PD, where PD is given by this one. Again, this PD will depend upon number of factors here. One is pitch line velocity, then the C is called the deformation factor of gear, which comes from the Young's modulus of both pinion and gear. So this one is not considered in case of the velocity factor. So that's why they included this one also, and E is also errors on the gear and pinion. So B is going to be the face width. That we know all these things. So where PD is the dynamic load and V is the pitch line velocity, C is the deformation factor. We'll see what is the formula for C also. E is sum of errors between the two meshing gear teeth. B is face width, and PD is the tangential force. So now, what is that formula for C? So the formula for C, that is the deformation factor, depends upon the moduli of velocity of the materials of pinion and gear, and is given by this formula. C is equal to K divided by 1 by EP plus 1 by EC. EP is nothing but the Young's modulus of the pinion. EG is the Young's modulus of the gear, and K is again a constant factor, and that constant will depends upon the form of our tooth. So that is K value is going to be 0.17 for 14.5 degrees full depth teeth, which is equal to 0.111 for 20-degree full depth teeth, 0.115 for 20-degree sub teeth. So that means once you know this K value, substitute this. If you know the Young's modulus of or modulus elasticity of gear and pinion, you can substitute into this equation. From that equation, you will get the C value. So once you know the C value, you can substitute into that. Then you have a error. Error is given as E is nothing but EC plus EP. Error on the pinion and error on the gear. So this is expressed as some phi expressed in terms of phi, which is nothing but the deviation of how much deviation is there in the invalid tooth profile for a given gear and pinion. So based on that, you can calculate this. Of course, if nothing is given, we generally will consider E is equal to 1. If they mention about this error, you consider it. We'll consider that. Otherwise, we can ignore this one. That means by taking E is equal to 1 in that equation, we can ignore it and we can find the dynamic load using Buckingham equation. Okay, right. So now we are in a position to calculate, we know how to calculate the beam strength, which is nothing but a static load. For that beam strength, we can add the dynamic load either by considering the velocity factor or by considering the Buckingham's equation. So if you use a velocity factor, so straight away you can convert that load, that is P effective is nothing but CS into your PT divided by CV. You will get the total load or effective load. We call it as effective load, that is nothing but the load due to PT plus load due to the dynamic conditions in the gear machine. So suppose if you don't want to use the velocity factor approach, if you want to go for the Buckingham equation, what you need to do is your effective load on the gear tooth is equal to CS into P plus PD, where PD is the dynamic load given by your Buckingham's equation. So using that Buckingham equation, you can calculate PD. So once you have these two, so finally you are in a position to calculate what is the effective load on the gear teeth. So once you know the effective load on the gear teeth, so using that we can design the gear. So that is our next topic. So estimation of the module based on this effective strength. It's not beam strength. Okay, you can call it as beam strength only, but effective load. So in order to avoid the failure of gear tooth due to bending, so this is the criteria. Your beam strength equation should be greater than, or your beam strength should be greater than your effective load. So then you can say the tooth is going to be safe. So then for this, what we will do is this greater than symbol can be replaced by considering some factor of safety. So introducing a factor of safety, then you can write this greater than symbol can be replaced by SB is equal to P effective into factor of safety. So that means the design criteria here is your beam strength should be equal to P effective into factor of safety. So then from that you can easily derive the module. So then what we do is whatever equations we derived so far, we will substitute those expressions into this. So from that you can easily derive what is the expression for module. So we want to find the module only. So we will derive the module. So for that here, generally the recommended factor of safety is 1.5 to 2. In case of this gear tooth, the recommended factor of safety is only 1.5 to 2. So therefore, now we'll try to using these conditions or by substituting SB value and P effective values, we'll try to find out what is the expression for the module of a gear. Yeah. So for that, first we'll take the expression for the PT. So because our P effective is consists of PT also, and also this PD comes from the torque transmitted and this torque comes from the power transmitted. So we'll try to substitute all these things so that you can get the equation for the module. So PT, we know PT is nothing but 2mt by d dash, which is nothing but your d dash is nothing but module into the number of teeth z. So and also this mt is nothing but 16 to 10 cube by 2 pi n. Or else if you want, since if you design it for pinion, you take PP here suffix speed. Or if you want to, if you are designing based on the gear, you have to take here GG. That it depends. So that we need to decide the first step. In the first step only you need to decide which one based on whether gear or pinion you need to decide. So you need to design the gear. So that is decided by which one is the weaker. Based on that you need to design. Suppose if both are made of same material, obviously the design is based on the pinion, we'll proceed PP. Or else you need to calculate sigma B, product of sigma B into Y, and based on that, first you need to decide whether gear is the weaker one or pinion is the weaker one. Based on the weaker one, you need to design it. Okay, so this is the expression for PT. So PT I can write in terms of power transmitted and module and number of teeth and speed in RPM. So this is the expression for PT. And also, if I consider the velocity factor approach, so then the effective load is nothing but CS by CV into PT. So if I substitute for this PT into this, so if I rearrange that, your P effective is going to be this one. Then for design criteria, the design criteria equation is SB is equal to P effective into FS. So in this equation, I'll substitute what is P effective, and also I'll substitute what is sigma B, SB. What is SB? SB we derived it as M into B into sigma B into Y, and also the sigma B I'll take it as something like SUT by 3. Sigma B allowable bending stress is SUT by 3, and here I'll make a little bit of modification. Like I said, always we'll express B is equal to some C times M. So therefore, your B by M will become constant. So to introduce that here, what I'll do is I'll multiply and divide this equation by M. So then if I multiply here at M square, M will become M square. I'm dividing it. So therefore, I'll modify this equation something like this. So now I'll take this equation, I'll substitute into this equation for SB. This is substituted on the left side. And then I'll take this and I'll substitute on the right side. Right? So now from this, I'll simplify this and I'll try to find, if I simplify this, I'll get an expression for module M. I'll get an expression for module M. So now if you rearrange these two equations after substituting SB like this and P effective is like this, and if you simplify this, you are going to get this is the equation for the module of a gear teeth. So that means, so using this equation, only one simple equation, using this equation you can design the gear. So only thing is provided if you know all these parameters. So in this, everything is known. So then if you know everything, what you should know is, you should know what is CS, you should know what is factor of safety, number of teeth on pinion, speed of the pinion, CV is the velocity factor. Of course, B by M is the constant ratio of that module to base width to the module, and SUT by 3 is nothing but the allowable bending stress, and Y is the Lewis form factor. So with this simple equation, if you remember this equation, you can easily derive it. Or if you don't know this equation, or you at least you need to know this procedure. So like that, you can design the gear. So this is how you can design a gear. Design of the gear is nothing but just you are estimating the module. Once you estimate the module, all other dimensions of the gear will fail in proportion with respect to module. So if I say addendum, dedendum, or root circle diameter, tooth circle diameter, whatever it may be, everything will be expressed in terms of M only. So all these parameters are in terms of module only. So addendum is one module. So that means if you know M, you will get one module or 1.25 module. Or dedendum is one module. Pitch circle diameter is nothing but module into number of teeth. Number of teeth is known, module is known. Then you can calculate pitch circle diameter. Like that, all the parameters of the gear can be identified once you know the module. So that means design of the gear is primarily finding out or estimating the module of the gear. Okay. So this is how we can estimate the module of the gear based on the beam strength, or based on the strength, we can say. Next, you have another approach, that is, like we discussed in the earlier class, gears are going to fail, or gear tooths are going to fail in two ways. One is due to excessive load, static and dynamic loads. So that can be avoided using this equation. If you are following this, if you design the gear tooth based on this equation, due to static and dynamic loads, you can avoid the failure if you design the gear based on this equation. The next kind of failure is due to surface destruction, that is due to wear. So that means next topic for us is how I can estimate the module of the gear based on wear strength, not on beam strength. It is now based on where we need to design. That we'll call it as estimation of the module based on wear strength. So before going into the estimate this module, first we'll try to find out what is the equation for the wear strength. Well, similar to the beam strength, we derive the expression for the beam strength. In a similar manner, we'll try to derive the expression for the wear strength. Then, based on that wear strength, we'll try to find out what is the module or what is the equation for module if you are considering the wear strength also. So that means you need to design the gear into two criteria. So either it has to satisfy both the criteria. You need to design the gear based on the beam strength as well as wear strength, so that you can avoid two types of failures. Okay, right. So first, then we'll see what is the wear strength first. Then we'll see how we can estimate the module based on its wear strength also. The failure of gear tooth due to pitting occurs when contact stresses between the two meshing teeth exceed the surface hindrance strength of the material. So that means the fitting failure will take place when the surface hindrance strength of the gear tooth is less than the contact stress. So due to pitting, a contact stresses will be induced in the surface of the gear tooth. These contact stresses, magnitude of this contact stresses are exceeds the surface hindrance, then the gear will worn out and gear tooth is going to be failed. So to avoid this, first we should know what is the wear strength, then how we can avoid this fitting failure. So fitting is a surface fatigue failure characterized by small fits on the surface of the gear tooth. So we already discussed about these wear failures, right? In order to avoid this type of failure, the proportions of the gear tooth and surface properties such as surface hardness should select in such a way that wear strength of the gear tooth is more than the effective load between the meshing tooth. So the approach is similar. In case of the beam strength, what we did is your effective load should be less than the beam strength of the gear. So then it is safe against the static loads. So now due to wear failure, if you choose the proportions of the gear tooth and its surface properties such that the wear strength of the gear tooth is more than the effective load on the meshing teeth. So earlier criteria is beam strength is more than the effective load. Now the criteria is wear strength should be greater than the effective load. So therefore that means, so to identify the expression for the module, you should know what is the wear strength of the gear, and also you should know what is the effective load of the gear also. So if you know these two things, then based on that you can easily derive an expression for the module and you can design the gear for the wear strength also. Right? So the analysis of wear strength was done by again Buckingham. So in his paper, the relation of load and wear of the gear teeth. So okay, anyway, he published that paper in 1926. Still, we are using that one. So to calculate the wear strength of a gear tooth. So that means we'll use again Buckingham's equations to find its wear. Remember that Buckingham equation, what is we use for the dynamic load? That is not the same as this one. This is different. That is different. Both are not same. So for the beam strength, in beam strength, whatever dynamic load you are considering, that is different. Even this is different. So don't confuse between those two. So even this load is that load is same. Don't take like that. Here, while calculating the wear strength of the gear tooth, he has used the theory of contact stresses that are proposed by these heads. So again, so we'll see what is this heads equation of contact stresses. Then how he used those equations to convert that one as a wear strength of the gear tooth. That we'll see now. So here, this is the picture which shows that two cylinders are pressed against each other. So they are pressing like this. So they are pressed against each other, and at the same time they are rotating like this. So because of this, at the contact surfaces of these two gears are two cylinders. Here, of course, here the edge contact stress is based on the cylinders, not based on the gears. So we'll take the formulas for the cylinders and we'll apply our analogy. some analogy to convert this one from the cylinders to the teeth, gear tooth, how we can modify that. So due to this, there is a contact stress is developed, and the contact surface here having a length of 2b, and the distribution of the stress is also, you can see that the stress is distributed in a elliptical way. The shape of stress distribution here is something like a ellipse. So now for this, we are not going to derive all these things, how we got this expression, all these things. Right away we'll take whatever heads is given for the contact stress for this condition, we'll take that. Based on that, we'll develop what is the equation we are going to use for the wave strength. So we are not going to derive the contact stress equation also. When two cylinders are pressed together against each other, the contact stress is given by, this is the formula. What H is given, sigma C is equal to this compressive stress here is 2P divided by pi into B into L. So where B is semi length, or 2B is going to be the total length of this contact area. So he has taken that B is given by this expression. He derived it. So it doesn't matter. We don't bother how we got these equations, all those things. So just we'll use this to derive our wave strength equation. So in this equation, if you want to see at the terminologies, P is the applied load, and then B is, just now I told, this is the contact area. In the contact area, it is taken half of B is nothing but the semi length of that contact area, and the expression for B is also given like this. So mu is the friction between these two cylinders. E1 and E2 are the Young's modulus of these two cylinders, cylinder 1 and cylinder 2. D1 and D2 are the diameters of these two cylinders. Smaller diameter is D1, bigger one's diameter is D2. So now here this is the equation he has given, and if you substitute this B into this equation, you will get, okay, this is the sigma C, maximum value of compressive stress, P is the pressing force, and half width of deformation. So half width of the deformation, we'll take it as B. L is the axial length of the cylinder. In this equation, L is also there. L is the axial length of the cylinder. D1 and D2 are the diameters of the two cylinders. E1 and E2 are modulus of mass of the two cylinders. U is Poisson's ratio. So now what we'll do is we'll substitute what is this B into this equation. If I substitute that, okay, so these are the sum of the part. Due to deformation under the action of the load P, a rectangular surface of width 2b and length 2l is formed between the two cylinders. So here, because of this one, a rectangular surface of 2b into L is formed here. The elliptical stress distribution across the width 2b is shown in figure B and C. Substituting the B value into this equation. So this is the expression for B as given. If you substitute that into this equation and squaring on both sides, you can write sigma C is equal to something like this. So here this D1 and D2 is replaced by R1 and R2. So relation is D1 is nothing but 2R1, D2 is 2R2. So if you substitute and rearrange this equation, he got sigma C square is something like this. So where R1 and R2 are the radii of the cylinders. But our question here now, how we can use this formula for our gears. So that for that, what we need to do is we need to compare these two cylinders to our two meshing gears. So of course, if you take mu is equal to 0.3, this equation is this value 1 by pi into 1 minus mu square comes out as 0.5. So that's what he has given. Okay. So now to compare our problem to that, here now these are the two contacting gears and they are meeting at the pitch point here. So now the radii R1 and R2 in the equation for the contact stress are to be replaced by the radii of curvature of these two gears. So here our R1 is nothing but radii of curvature of the pinion, R2 is the radius of curvature of the gear, which is nothing but here if you take this radius of curvature, if the pitch angle is alpha in both the cases, so you can easily find out this dp by 2 sin alpha and dz dash by sin alpha by 2. R1 and R2 are replaced in that formula for contact stresses. Your R1 and R2 expressions are this one. And also we'll define one more factor which is called as a ratio factor Q, which is defined as 2 times Z into ZZ divided by ZG plus ZP, where ZZ is nothing but number of tooth on the gear and ZP is the number of tooth on the pinion. So in this case, The same thing you can know. So if you know, we know the relation between module and pitch circle diameter. Pitch circle diameter is nothing but m module into number of teeth. So here the same thing can be written something like this. That means, so here I can write, I will multiply this one by m on numerator and denominator. If I do that here, then what I'll get? 2 into m into zg is nothing but your dz, that is pitch circle diameter of the gear. Even m into zg is nothing but pitch circle diameter of the gear. M into zp is nothing but pitch circle diameter of the gear pinion. So that means, so these two equations are same. So this is this equation is in terms of gear tooth, and this equation is in terms of pitch circle diameter, but both are same. That means you can define this factor q as either 2 zg by zg plus zp or 2 dg by dg plus dp. So either way you can do it. But here what we'll do is, in our equation we have r1 and r2, so which is also expressed in terms of dp and dg. So now what we'll do is, we'll try to substitute this one in this form, something like this. Suppose if I take 1 by dp plus 1 by dg, I can write this one as this. If I simplify this, it is going to be this one only, dg plus dp by dg into dp. So but what is this value, dg into dg plus dp by dg into dp? From this what we get is only, so dg by dp into dg, so that is this value. So this quantity is nothing but your 2 divided by q. So therefore we will get 2 divided by q into dp dash. So we will introduce this q factor so that we can simplify this one r1 and r2 expressions only. So therefore your 1 by r1 plus 1 by r2. So that means here dp is there. If I divide this one by 2, so I'll get the diameter radii. So then I'll get, or else we have an expression for radii r1 r2 also here. So if I substitute these two here into this, and if it is further simplified, then you can write 1 by r1 plus 1 by r2 for a gear tooth meshing of gear tooth as 4 divided by q dp dash sin alpha. Once you know this, then other things. So then what is the p value? In our contact stress, we have expression for p also. Yeah, or else here if I take this one. So in this, we identified this one now. We got an expression for 1 by r1 plus 1 by r2. This is known. If you know the material modulus, then this is also done. Then you need to identify what is P, what is L. So if you identify that, then you can calculate the contact stress value for our gears also, gears which are in mesh. So then P is nothing but the force here, the resultant force, we know that always it will act along the pitch line, and the resultant force is nothing but Pn only. So we know this. And also we know Pt is nothing but relation between Pt and P, and Pt is nothing but Pn by cos Pt cos alpha. So this is the relation, we know this one also, right? So therefore our P is nothing but Pn here, the resultant force acting at the pitch line is Pn, but we want to express that Pn in terms of Pt, so therefore it is comes out as Pt by cos alpha. So now P is known, then the last thing is only L. So in this equation now we know everything. We know this value, we know this value, we know the P, and we know, anyway these are constants only this L. L is nothing but the width of the gear tooth along this surface, which is nothing but base B, face width B. So therefore our L is equal to B in case of this gear tooth. So now once I know everything, I can substitute all these parameters into that contact equation. If I substitute that, the contact stress is given as by this equation, 1.4 into Pt divided by B into Q into dP dash sin alpha cos alpha into 1 by E1 plus 1 by E2. Again, this value, that is Pt, a load stress factor K, is defined as something like this. If I take sigma C multiplied by sin square alpha plus cos square alpha into this one, that means this portion I will bring it to this side. Then the entire thing is denoted by some K, and also of course this 1.4 is also there. So then we'll denote that one by K. Then you can write it as K is equal to our Pt. So from this, Pt is equal to B into Q dP dash. Those things are there, and remaining term is nothing but K only. So that means why we are written like this is just similar to our beam strength equation, SB what we written beam strength equation is something like m into b into sigma b into y. So here also similarly, in a similar line, we want to write something like that. So that's why we substituted for this k into for this expression, and we written the PD as something like this. So now B, Q, dP dash and K. So here you can easily estimate the K value. So how you can estimate the K value? K is going to be sigma C is going to be the allowable compressive stress in a given material, and you should know what is the Young's modulus of gear 1 and gear 2, and also what is the pressure angle. So remaining things are constants only. You can calculate K value easily based on the materials and based on the materials of the gear and pinion, and also pressure angle. You should know pressure angle of the gear. So then once you know the K value, then you can calculate this PT. So now this PT will depends upon, see, for a given gear B, Q and dP, they are constants, only it depends upon K. The equation gives a relationship between the tangential force PT and the corresponding constant stress, contact stress sigma C, or here in terms of K, either K. So if this PT increases, K or K increases, PT will increase, or PT increases, K will increases. So therefore, when the tangential force is increases, the contact stress will also increases. So that means this equation will give you a relationship between the tangential force and the corresponding contact stress. Okay. So pitting occurs when the contact stress reaches the magnitude of the surface endurance strength. So then if you avoid the failure, your surface endurance strength should be more than this contact stress. So the corresponding value of PT is called the wear strength. So that means if you replace this PT by wear strength, that is SW. So therefore wear strength is the maximum value of tangential force that the tooth can transmit without fitting failure. So again, wear strength is nothing but it is a tangential force only. So earlier we discussed beam strength. That beam strength is also tangential force. Even this is also tangential force, but for the tangential force we are applied different factors for beam strength. Here we applied different factors. That is the only thing here. But total always the tangential force is going to be remain same. Or the criteria is only the tangential force in both wear or the beam strength also. Right? So the wear strength is the maximum value of tangential force that the tooth can transmit without fitting failure. So replacing PT by SW, you can write the expression for the wear strength of a gear tooth. SW is equal to B into Q into dP dash by dP dash into Q. So this is what we call it as a Buckingham's beam strength, wear strength equation. Buckingham's wear strength equation, not beam strength equation, wear strength equation. That's why here this W stands for wear, S for strength. In case of beam strength, we have taken SB, B for beam, and S is strength. Here W for wear. So now based on this, we can. So now we calculated the wear strength. But what is what we said in the beginning? To design that, this wear strength should be greater than your P effective. This should be greater than your P effective. Then you can say that your gear is going to be safe. So then what is P effective here again? So you need to calculate that. Based on that, you can derive the expression for the module also here based on wear strength also. So here where SW is wear strength of the gear tooth, sigma C is the surface endurance strength of the material. Equation SW is known as Buckingham equation for the wear. Okay, so that's what we already discussed. Okay, right. So now what next step is you need to find out what is P effective. So for that, in order to avoid the failure of gear tooth due to pitting, your SW should be greater than P effective. Your SW should be greater than P effective. So then, like similar to the beam strength, here also we'll consider the factor of safety. Then if you consider this greater than symbol is replaced by equal to sign, SW should be equal to P effective into Fs. So a recommended factor of safety here also again 1.5 to 2. So then the same thing what we done in case of beam strength, that is the repetition. So first we'll write an expression for PT in terms of power transmitted and number of teeth and module of the gear or pinion. So N. Then we try to find out the P effective expression. It is same what we did in case of beam strength, same here. CS by CV into P. If you want to use velocity approach only, see here, if you use velocity factor approach only, you will get like this. If you want to go for the precise one, that is Buckingham equation, you need to modify that. So depends upon the problem. Suppose if you say use velocity approach, you have to use this equation to calculate P effective. If you say Buckingham equation means your effective P effective is nothing but CS into PT plus PD. So PD equation is given by the Buckingham. You need to use that equation. Okay, you keep that point in your mind, right? So now I know the effective load P effective. So then you have an expression for wave strength. Just now we derived. So we'll rearrange this wave strength is something like m into just multiplying the multiplying and dividing by m. This equation you can write this one as something like this. So this will cancel out, and Q is, you can dP you can write as m into Zp. We know that spherical diameter is nothing but module into number of teeth, and K remains K. So then we'll take this equation and this equation, P effective equation, this equation, we'll substitute that into this equation. Then if you substitute and rearrange this equation, I can derive an expression for m, that is module, which is going to be something like this. Okay, so using this equation, you can derive or you can find the module based on the wave strength. So earlier equation is based on wave strength, now this equation is based on wave strength. So therefore, suppose if they ask you to design the game based on the wave strength, you have to use this equation. Based on beam strength, you have to use the earlier equation. Okay, right. So this is how you can design the game. So now what we'll do is we'll take up some numerical problems and then we'll try to discuss those numerical problems also. So in that, this is going to be the first problem. So first note it down this problem and we'll try to discuss the solution. Then if time is there, we'll take up one more problem also. So note it down. Once it is completed, just intimate me so that we'll discuss the solution. Okay, is it over? Is it over or not? If nobody is responding, check whether they are there in the class or not. No, some people are there in the class, but nobody is responding. Did you note it down? చెప్పాలి కదా అయిపోయిందా అంటే లేదు సార్ రాస్తున్నా అని చెప్పాలిగా. ఓకే, డూ ఇట్.
Sir.
Okay, right. So we'll see the solution for this now. Okay, so first I'll read the problem, then we'll discuss the solution. It is required to design a pair of spur gears with 20-degree full depth involute tooth. So this is what the type of tooth what is used, and the design should be based on Lewis equation. So that is, Lewis equation means your design should be based on beam strength. Then the velocity factor is to be used to account for the dynamic load. Even that is statement also is given in the problem. You need to use velocity factor to determine the effect of dynamic load. The pinion shaft connected to a 10 kilowatt 440 RPM motor. So pinion is rotating at 440 RPM and power transmitted is 10 kilowatts. And he has given the starting torque of the motor is 150% of the rated torque. So that means he indirectly has given the service factor CS. So starting torque divided by the rated torque. So 1.5, 150% means it is 1.5. The speed reduction is 4:1. That is, the speed reduction is nothing but the velocity ratio is 4:1. So that means if the pinion runs at 1440 RPM, your gear should run at 1/4 of that. So speed is reduced here. Reduction means 1440 is become 1440 by 4 at the driven end. Driving number is the motor here. The gear, driving gear runs at 1440 RPM. So at the driven gear, the speed should be 1440 divided by 4. That's why we call it as a speed reduction, means speed should be reduced there at the driven shaft. So it becomes 1440 by 4. The pinion as well as gear is made of plain carbon steel 40C8 with SUT is equal to 600 Newton per mm square. So he has stated that both pinion and gear are made of same material only. So then the first criteria you can easily identify if both are made of same material, pinion obviously pinion is going to be the weaker one. Straight away you can take and you can design the gear drive based on pinion only. Then the SUT for that gear material is given as 600 Newton per mm square. Then the factor of safety can be taken as 1.5. He has given the factor of safety also 1.5. So that means using this factor of safety, you can calculate what is allowable stress sigma b, or even you can use this factor of safety to calculate the effective load also. Okay, then what you ask is design the gears, specify their dimensions, and suggest suitable surface hardness of the gears also. Here, the surface hardness of the gears. Surface hardness comes from wear point of view. So that means based on the wear strength equation, you need to calculate what is the surface hardness required. So we'll see all these things one by one. So now we'll see step by step the solution for this problem. First, we'll identify the data, what he has given in the problem. We'll write that. So, power transmitted is 10 kilowatts. So, kilowatt is equal to 10 means the power is 10 kilowatts. N or NP, you can take a N speed of the pinion here, which is 1440 RPM. Speed ratio is 4, he has given 4 here. SUT is 600 Newton per mm square. Fs is 1.5. Starting torque is equal to 150% of rating torque. So everything whatever he has given in the problem, we written the steps. So then the first statement, first thing is you need to estimate the module based on the beam strength. So Lewis equation is nothing but your beam strength based on beam strength only. So you need to estimate the module based on this beam strength. So for that, first you need to identify the weaker one. Like I said, the first statement is corresponding to that only. Since both gears are made of same material, the pinion is the weaker than the gear. The minimum number of teeth for 20-degree pressure angle is 18. So this is also important. So you need to, if he has given the number of teeth on the gear pinion, you can take that. But he has not given that in this problem. So then what you have to do is you need to assume the gear teeth. So for that, the minimum number of teeth for 20-degree pressure angle is going to be 18. So if you recall, I think in your kinematics you might have studied about interference, all these things. There, the minimum number of teeth on a gear to avoid interference is given by 2 by sine square alpha. So this is the formula. 2 by sine square alpha. This is the minimum number of teeth. T minimum or Z minimum. So Z, we are using Z symbol. So Z minimum is equal to 2 divided by sine square alpha. If you substitute alpha here 20 degrees into this, we get it is around 17. We get it as 17. So this is the formula you need to use. So therefore we choose the minimum number of teeth, odd number, even number, which is 18. So that means we know the number of teeth on the pinion. So if you know the number of teeth on the pinion, since he has given the velocity ratio, based on that you can calculate the number of teeth on gear also. So number of teeth on gear is nothing but your G is nothing but speed ratio into ZP only. So this is going to be the ZG value. So those two calculations I will show it now. ZP is 18 and ZG is I into ZP. 1 minute. Okay, so we calculated number of teeth on pinion as we assumed we consider the number of teeth on pinion as 18 and calculated number of teeth on gear as 72. Then the torque, because we need to calculate what is P effective. Here the beam strength equation is also based on P effective only. You need to calculate P effective. So for that you require MT. MT is formula is this one. 16P divided by 2 pi Np. So we substitute power transmitted is 10 kilowatts and speed of the pinion is 1440. If you substitute that, the torque transmitted is comes out as this much. Of course, here the decimal point is there, that is missing. 66,314.56 Newton mm. Since I am substituting here 10 power 6 factor, so whatever we got it is, that is going to be in Newton mm only. Okay, so I got the MT value. Then Lewis form factor we need to take. So now this comes from the data book again. So for 18 teeth, number of teeth is 18 and the full depth 20-degree pressure angle gear tooth. So you have to take that. So I think in our data book, so these are not given. The problem is again like they will have some table which are not given in the chain drives. Here also the same thing. These things are not given. So this Lewis form factor, Lewis equations are not given in your data book. So I think an old edition is not given. Maybe in new edition also is not given. So those who have a data book with you, just open and you tell me whether he has given this one or not. Okay, so open chapter number. I think I already talked with the examination sections. They are providing as a supplement. This one as a supplement for our examination also. So therefore, whatever is there, directly you can use that those supplement. In the supplement, you can calculate what is the y value. Or before that, okay, I want to check whether it is there in our data book or not. In the new edition, whether he has given that one or not. So for that, just you open the chapter number 25 for me. It is spur and helical gear drives. So in new edition, what is the chapter?
28.
28 Emma 28
అవును సార్ 28 సార్
28 ఓపెన్ చేయండి. సో అంత డేటా బుక్ ఓపెన్ చేయండి. మీ దగ్గర ఉన్న వాళ్ళు డేటా బుక్ ఓపెన్ చేయండి. I'll tell you some formulas what we are going to use in this data book also. But all are not available. Some of them are available. So we'll discuss those things. So first he has given the symbols. B, small b, face width, capital C, center distance, small c, bottom clearance, D1, D2, pitch circle diameters of pinion and gear, DA1, DA2, DF1, like that, E1, E2, H, HA, HF, I, K, KD, like that. So many things are is given. MT, but see, you can see pitch circular pitch formula also has given. Circular pitch also PC is equal to pi into d by z. Diametral pitch formula is also given. PD is equal to z by d, like that he has given. Small y, in that notation if you see small y, which is form factor, then YV is form factor for virtual number of teeth. Z1, Z2 number of teeth on pinion and number gear. ZV virtual number of teeth. Alpha pressure angle. So alpha is equal to 20 degrees, standard value, like that he mentioned. Beta, sigma B, sigma C again. Then psi, ratio of face width to center distance, B by C. Psi M, pi, progression ratio or step ratio. Like that, he has given the notations or symbols. Then if you come to the design particulars and equations page, in that the first one, normal twisting moment transmitted by the pinion. So here he used MT. So some notation ఇంతకుముందు అన్నిటికి టార్క్ T అన్నాడు, ఇక్కడికి వచ్చేసరికి MT తీసుకుండు. So whatever formula we used it here, you can see the same thing here. Anyway, I will put into presentation mode so that I have a pen access to me. Okay, so whatever formula we write it here. This formula is as it is there. Only thing is instead of NP, he has taken it as N1. That is the only thing. MT is equal to 60 into 10 power 6 into P. P is nothing but power. We are taking kilowatt. He has taken it as P divided by 2 pi N1. Same formula. Where P in kilowatts and N1 in RPM. Like that also has given. Then design twisting moment. MT equal to MT into K into KD. So initial design, what he said is assume K into KD as 1.3, like that he has given. But we follow beam strength based on the other way, so we'll follow that one only. So then next module based on beam strength of a weaker gear. So he has given one formula, but we are not going to follow that formula. So no, don't use those formulas to calculate. So that means first next three formulas are not useful to you. Even for compressive stress also it is a different one. We are not going to use those things. Number of teeth, you can take that also. That formula you can use it. Center distance, m into z1 plus z2 by 2. That also you can use. Addendum for standard teeth is equal to HA equal to 1 module. That's what he has given. So like I already said, if you know the module, you can calculate addendum also. Addendum is nothing but 1 module. Whatever may be the module value, that is going to be the addendum. Then if you flip the next page, he has given addendum for the standard tooth HF, which is 1.25 m, tooth height 2.25 m, height factor 1 for standard teeth, 0.8 for sub teeth, like that he has given. Bottom clearance values is given. Pitch circle diameter formulas are given. Yeah, D1 is equal to m into Z1 and D2 is equal to m into Z2. Then tip circle diameter means addendum circle diameter. Root circle diameter means addendum circle diameter. Those also given. Then transmission ratio I. Here we use this one. This is this formula. I is Z2 by Z1, which is equal to D2 by D1, which is equal to N by N1, N1 by N2. So what Z1, Z2 lo pechadu, manam ZP and Z gear antunnamu. That is the only difference. Then circular pitch, PC is equal to pi d by Z, diametral pitch PD is equal to Z by D. Progression ratio is not required for you. Suppose if you want to draw the profile of the gear tooth, the next page he has given the figure. So if you want to draw it in the examination, just copy it from this page. So that is okay. So only that much is given. If I go for the next page, he has given helical and herringbone gears. So that means next page data corresponding to the helical gears. So right now we are discussing about only the spur gears. So you can use only those formulas what he has given here. Other than that, do you have anything in your data book? New edition lo ఏమన్నా ఉందమ్మా?
లేదు సార్ అంతే సార్.
Okay, so దాని తర్వాత you can go for next 2 pages helical gear drives ఉన్న తర్వాత ఫిగర్ ఉన్న తర్వాత నెక్స్ట్ పేజ్ కి వెళ్ళండి. డిజైన్ స్ట్రెస్ ఫర్ గేర్ మెటీరియల్స్ అని ఇచ్చాడు. ఉందా? టేబుల్ 25.1 అంటే ఫస్ట్ టేబుల్. ఆ చాప్టర్ లో ఫస్ట్ టేబుల్ ఏముందో చూడండి. ఫస్ట్ టేబుల్ 25.1 ఫర్ మీ, మేబీ మీకు 29 అంతా అంటారు చాప్టర్. దాంట్లో టేబుల్ చూడండి ఏముందో. చూస్తాను రా, ఎవడే రెస్పాండ్ అవట్లా. ఏంట్రా క్లాస్లోనే ఉన్నావా? డిస్కనెక్ట్ అయిందా? ఉంది కదా క్లాస్లోనే. ఎవరి దగ్గర లేదా డేటా బుక్? ఎవడు రెస్పాండ్ అవ్వడు? 30 మంది ఉన్నారు క్లాస్లో, ఒకడు కూడా రెస్పాండ్ అవ్వట్లా.
Yes, sir. ఉంది సార్ డిజైన్స్ as per gear materials.
ఉందా?
ఉంది సార్.
నేను 1 సార్లు అడిగితే అప్పుడు ఎక్కువ చెబుతాను. ఓకే. సో ఇప్పుడు మనకి ఇచ్చిన ప్రాబ్లంలో డిజైన్ 600 ఎంపీఆర్ 600 Nm/m² అని ఇచ్చాడు ఈ ప్రాబ్లంలో. సో సపోజ్ ఒకసారి ఇవ్వకపోవచ్చు, అది గేర్ మెటీరియల్నే స్పెసిఫై చేయొచ్చు. ఇక్కడ ఈ ప్రాబ్లంలో ఇక్కడ ఇట్ ఈస్ 40 C8 విత్ SUTs 600 Nm/m² అని ఇచ్చాడు. సపోజ్ ఇవ్వలేదు అనుకో, what you have to do? You have to take that one from this table. డిజైన్ స్ట్రెస్ అని కాలం ఉంది, లాస్ట్ కాలం ఉంది చూడండి దాంట్లో. సో దాంట్లో ఇచ్చాడు మీకు 460, 550, 700, సిగ్మా సి 500, 600, 700, 750 బ్రాకెట్స్లో ఇచ్చాడు. సో గ్రేడ్ 20 క్యాస్ట్ ఐరన్ అయితే గ్రేడ్ 20, గ్రేడ్ 25, గ్రేడ్ 35. సో అదే గ్రేడ్ 35లో ఈ ట్రీటెడ్ అయితే మీకు సిగ్మా సి వాల్యూస్ అక్కడ ఇచ్చాడు. అలా కాకుండా స్టీల్ అయితే C45 అండ్ Ni2 Cr1 40 Ni2 Cr1 M028 లైక్ దట్ వాటికి కూడా ఇచ్చాడు. సో అట్లా ఓన్లీ మెటీరియల్ స్పెసిఫై చేస్తే ఈ టేబుల్ నుంచి ఆ మెటీరియల్ ప్రాపర్టీ తీసుకోవాల్సి ఉంటుంది. సో దట్ ఈస్ వన్ థింగ్. అఫ్ కోర్స్ ఈ ప్రాబ్లంలో వాడు ఇచ్చాడు కాబట్టి నా ప్రాబ్లం లేదు. దెన్ నెక్స్ట్ దానికి వెళ్ళండి. నెక్స్ట్ టేబుల్కి వెళ్తే రికమెండెడ్ సిరీస్ ఆఫ్ మాడ్యూల్స్ ఇన్ ఎంఎం. సో మాడ్యూల్ ఏది పడితే అది తీసుకోకూడదు. సో వాడు ఇచ్చిన వాల్యూ దగ్గరికే రౌండ్ ఆఫ్ చేయాలి. సపోజ్ ప్రాబ్లం సాల్వ్ చేసినాక మనకి ఏదో ఒక వాల్యూ వచ్చింది. సో ఆ వాల్యూని ఎక్కడికి రౌండ్ ఆఫ్ చేయాలనేది దీన్ని బేస్ చేసుకుని చూడాలి. సో ప్రిఫర్డ్ వాల్యూస్ ఏంటి? 1, 1.25, 1.5, 2, 2.5, 3, 4, 5, 6, 8, 7 లేదు. సపోజ్ నీకు ప్రాబ్లంలో మాడ్యూల్ క్యాలిక్యులేట్ చేస్తే నీకు 6.4 వచ్చింది. దెన్ దాన్ని రౌండ్ ఆఫ్ చేసేటప్పుడు 7కి రౌండ్ ఆఫ్ చేయకూడదు. యూ హ్యావ్ టు రౌండ్ ఇట్ ఆఫ్ టు 8. సో బికాస్ after 6 preferred number is only 8 per module. So like that 10, 12, 16, 20, 25, 32, 40, 50. So you have to use this table to round it up to the next preferred number. So keep that point. So for that you require this table. So you can use this table also. Then mechanical property, next table, come to the next table. What he has given is mechanical properties of commonly used gear materials. So carbon steels, grey cast irons. So ఇక్కడ కూడా ఇచ్చాడు నీకు allowable stress, tensile strength ఇచ్చాడు, yield stress ఇచ్చాడు, BHN కూడా ఇచ్చాడు, modulus of elasticity కూడా ఇచ్చాడు, E ఇచ్చాడు. సో ఇందాక వేర్ ప్రాబ్లమ్స్ వేర్ స్ట్రెంత్ డిస్కస్ చేసినప్పుడు E1, E2 లోని ఆ ఫార్ములాలో ఇక్కడ ఈ టేబుల్ నుంచి నువ్వు యూ హ్యావ్ టు టేక్ దోస్ E1 and E2 వాల్యూస్. అట్లానే BHN, that is our surface hardness also you can pick it from this table also if required. సో అలానే రెండింటికి ఇచ్చాడు, స్టీల్స్కి ఇచ్చాడు, గ్రే కాస్ట్ ఐరన్కి ఇచ్చాడు. దెన్ నెక్స్ట్ టేబుల్కి వెళ్తే స్టాండర్డ్ గేర్ రేషియో I. సో గేర్ రేషియో ఎలా ఉందో స్టాండర్డ్ వాల్యూస్ ఏంటి అనేది ఇచ్చాడు మీకు. సో సింగిల్ స్టేజ్, డబుల్ స్టేజ్, ట్రిపుల్ స్టేజ్కి స్టాండర్డ్ రిడక్షన్ వాల్యూస్ ఇచ్చాడు. ఎనీవే సో దీన్ని పెద్ద ఉపయోగించి మనం దాంట్లో ఒకవేళ అది కూడా ఇవ్వకపోతే, గేర్ రేషియో కూడా ఇవ్వకపోతే యూ హ్యావ్ టు అజ్యూమ్ బేస్డ్ ఆన్ దిస్, యూ నీడ్ టు అజ్యూమ్ దిస్ ఇస్ ద gear ratio standard values. So in our problem he has given the 4 is going to be standard value for a single stage. You can see that only a pair of spur gears means it is a single stage gear train. So 4 he has given, so 4 is there in the table, so you can see that also. If that is also not mentioned, you have to take that value from this table. You cannot take randomly any other value, so you have to use only this. Then equivalent Young's modulus formulas also given, 2E1 E2 by next table, 2E1 E2 by E1 plus E2, like that you can take it. So then next table is type of gear transmission of open type gearing, speed reducers or something like some table is given. So but below that for light and medium duty B should be less than D1, for heavy duty B should be less than or equal to 1.5 D1. So B is nothing but phase width, D1 is the pinion diameter. Recommended values for psi also is given. Anyway, that we are not going to use. Even this is also to a table 25.6, 25.7 is if you follow the design based on the formula what he has given in the data book. Anyway, we are not following that. We don't want to use that one. Now, if you come to the next page, you can see that there he has given table 25.8. So, can somebody tell me what is there in that heading in the for the table? ఏముందిరా నెక్స్ట్ టేబుల్ ఏముంది? ఎవరు మాట్లాడలా మళ్ళా అసలు మీరు క్లాస్లో ఉన్నారా ఏం చేస్తారో అయితే ఎవరికి అర్థం కాదు. వాడు అక్కడ ఎవడో ఒకడు రెస్పాండ్ అవుతాడు, వాడు సైలెంట్ అయితే ఇంక ఎవడు మాట్లాడు. అరే 316 ఉన్నారా క్లాస్లో? మెసేజ్ పెట్టగా మాట్లాడి మైకా చేసి యూజ్లెస్ వల్ల. తేడా బుక్ ఉందా నీ దగ్గర? టైప్ చేయ వాల్యూస్ టేబుల్ ఏముందో టైప్ చేయలేదు అక్కడ. ఒక 30 మంది ఉన్నారు క్లాసులో, ఒకడు నోరు ఇప్పుడు ఉందా లేదా అని. అరే హర్ష ఉందా నీ దగ్గర డేటా బుక్? 355. ఉన్నా క్లాసులో అసలు? ఎరా టైప్ చేయారా టేబుల్ ఏముందా 316? what is the table you have? You type the heading of the table. $351.
Yes, sir.
ఉందా డేటా బుక్ నీ దగ్గర?
Soft copy ఉంది సార్.
ఏ నెట్ కేసు కొట్టుకోండి సాఫ్ట్ కాపీ. దేని మీద కొత్త సాఫ్ట్ కాపీ? $307 LE7
ఉంది సార్.
ఓ ఏముందమ్మా టేబుల్ చెప్పు దాంట్లో. ట్వంటీ ఓల్డ్ ఎడిషన్ న్యూ ఎడిషన్ నీ కాడ ఉంది?
న్యూ ఎడిషన్ సార్.
ఇది అప్పుడైతే 29 చాప్టర్ నెంబరు.
ఎస్ సార్.
29.8 టేబుల్ ఓపెన్ చేయి. ఏముందో చూపు.
డైనమిక్ లోడ్ ఫ్యాక్టర్ సార్.
డైనమిక్ లోడ్ ఫ్యాక్టర్ ఉందా? దానికి ముందు ఫామ్ ఫ్యాక్టర్ వై టేబుల్ లేదు అసలు.
28 చాప్టర్ సార్.
28
సార్.
అదే ఏదైతే పర్ గేర్ సంబంధించిన చాప్టర్ ఏదైతే అది ఓపెన్ చేయి.
ఫామ్ ఫ్యాక్టర్ 5 28.13 లో ఉంది సార్.
28.13
లో సార్.
టేబుల్స్
ఓపెన్ చేయండి. ఏముంది దాంట్లో చూడండి. ఫామ్ ఫ్యాక్టర్ ఉంది. తర్వాత ఏముంది?
ఫామ్ ఫ్యాక్టర్ y ఫర్ ఆల్ఫా ఇస్ ఈక్వల్ టు 20 అండ్ f నాట్ స్టార్ ఇస్ ఈక్వల్ టు 1 అని సార్.
ఎఫ్ నాట్ స్టార్ అంటే ఏంటంటే ఎఫ్ నాట్ ఇస్ ఈక్వల్ టు 1 అంటే ఇది ఫుల్ డెప్త్. ఆ టేబుల్ కింద ఇచ్చాడు చూడు. ఫర్ హైట్ ఫ్యాక్టర్ f0 ఇస్ ఈక్వల్ టు 0.8 in brackets sub teeth the above value should be divided by 0.8 అని క్లియర్ ఇచ్చాడా? ఉందా?
ఎస్ సార్ ఇచ్చాడు సార్ పేజ్ లాస్ట్ లో.
ఎస్ సార్.
ఇక్కడ ఇప్పుడు ఏంటంటే యూ హ్యావ్ 2 types ఆఫ్ గేర్స్. ఎక్స్టర్నల్ గేర్ ఉండొచ్చు, ఇంటర్నల్ గేర్ కూడా ఉండొచ్చు కదా. ఐడియా ఉందా ఎక్స్టర్నల్ గేర్ ఇంటర్నల్ గేర్ అంటే?
Yes, sir.
సో బేస్డ్ ఆన్ దట్ యూ నీడ్ టు టేక్ ది వాల్యూస్. సో యానలస్ అంటే ఇంటర్నల్ గేర్. ఓకే, సో ఇప్పుడు నీకు చూడు బేస్డ్ ఆన్ నంబర్ ఆఫ్ టీత్ యాస్ గివెన్. సో మనకి ప్రాబ్లంలో ఇచ్చింది ఏంటి? ఆల్ఫా 20 degrees కదా ఇచ్చింది. ప్రెజర్ యాంగిల్ ఈస్ 20 degrees. ఇన్ ద ప్రాబ్లంలో చూస్తే క్లియర్గా ప్రెజర్ యాంగిల్ ఈస్ 20 degrees ఫుల్ డెప్త్. సో ఫుల్ డెప్త్ కాబట్టి ఉన్న వాల్యూస్ యాక్చువల్లీ తీసుకోవచ్చు నువ్వు. కానీ ఏం చేయాలి? అదే సబ్ టూత్ అయితే దాన్ని 0.8 పెట్టి డివైడ్ చేయాలి. ఉన్న ఫ్యాక్టర్ని 0.8 పెట్టి డివైడ్ చేయాలి. అంతేనా? ఆ టేబుల్ ఉద్దేశం అదేనా? వాడు కింద ఇచ్చిన దాని ఉద్దేశం అదేనా?
Yes, sir.
కాకపోతే ఆ టేబుల్లోనే ఇంకోటి ఇచ్చాడు. వాడు ఏమి ఇచ్చాడు? బ్రాకెట్లో ఒకటి ఇచ్చాడు. ఏమి ఇచ్చాడు? వై ఇంక్లూడ్స్ కాస్ ఆల్ఫా టామ్ అని ఇచ్చాడా క్లియర్గా?
Yes, sir. ఇచ్చాడు సార్.
అంటే ఏంటి? మనం తీసుకున్న ఫ్యాక్టర్ వేరు, ఈడు ఇచ్చిన ఫ్యాక్టర్ వేరు. మనం డిఫైన్ చేసింది ఏంటి? వై అనేది మన డెరివేషన్లో. ఐ టేక్ యూ బ్యాక్ టు ద డెరివేషన్. See here, y is equal to t square by 6hm, right? So ఇది మనం y డిఫైన్ చేసింది మనం. We define y something like this. Y is equal to t square divided by 6hm. కానీ వాడేమి ఇచ్చాడు? వాడేమంటాడు? దీంట్లో మనకి ఎక్కడ కాస్ ఆల్ఫా కానీ సైన్ ఆల్ఫా కానీ ఏమి లేదు దీంట్లో. బట్ ఇక్కడ ఇచ్చిన టేబుల్లో దిస్ ఫ్యాక్టర్ వై వాల్యూస్ ఆల్సో ఇంక్లూడ్స్ కాస్ ఆల్ఫా టామ్ అని ఇచ్చాడు క్లియర్గా. అంటే అది కాస్ ఆల్ఫా ఎట్లా ఇంక్లూడ్ అయింది అది చెప్పలేదు వాడు మనకి. సో ఏమి ఇచ్చాడు? జస్ట్ వాల్యూస్ ఇచ్చాడు. వై ఇంక్లూడ్స్ కాస్ ఆల్ఫా టామ్ అన్నాడు. ఇప్పుడు మన ప్రాబ్లంకి వస్తే ఇప్పుడు ప్రాబ్లంలో నాకు వై వాల్యూ కావాలి ఇక్కడ. సో నెక్స్ట్ బీమ్ స్ట్రెంత్ ఏంటండి? నెక్స్ట్ బీమ్ స్ట్రెంత్ వాల్యూలో మనకి వై వాల్యూ వస్తే బీమ్ స్ట్రెంత్ క్యాలిక్యులేట్ చేయగలరు. సో నౌ హౌ ఐ కెన్ పిక్ వై వాల్యూ నౌ ఫ్రమ్ దిస్ టేబుల్, from this book, data book. That is the next question. So ఇక్కడ వచ్చి ప్రాబ్లం ఏంటంటే సింపుల్గా నేను 0.308 అని చెప్పేసాను. ఓకే, లెట్ మీ టేక్ టు దట్ ప్రాబ్లం. ఎస్. సో ద లూయిస్ ఫార్మ్ ఫ్యాక్టర్ ఈస్ 0.308 by 18th teeth అని ఇక్కడ స్టేట్మెంట్ రాసాము. కానీ ఎట్లా వచ్చింది? ఇక్కడ 0.308 ఎలా వచ్చింది? సో దానికి ఏం చేయాలి? నీకు మళ్ళా నీకు టేబుల్లో ఇచ్చాడు ఏంది? అడెండమ్ మోడిఫికేషన్ కోఎఫిషియంట్ ఎక్స్ అని దాని వాల్యూస్ కూడా ఇచ్చాడు. మళ్ళీ -0.6 -0.4 -0.2 0 +0.2 +0.4 +0.6 +1.0 అని ఇచ్చాడు. సో అవి ఏమి లేకపోతే అంటే అడెండమ్ మోడిఫికేషన్ ఫ్యాక్టర్ లేకపోతే యూ హ్యావ్ టు చూస్ ఇట్ యాజ్ 0. 0 ఉన్న కాడ నీకు 18th teethకి ఎంత ఉంది? ఇక్కడ లూయిస్ ఫార్మ్ ఫ్యాక్టర్ బై ఎంత ఉందమ్మా? లూయిస్ ఫార్మ్ ఫ్యాక్టర్ ఎంత ఉంది?
0.377 సార్.
0.377 ఉంది అంతేనా? సో కానీ ఇక్కడ మన ప్రాబ్లంలో ఎంత తీసుకుని ఎంత వచ్చాయి? ఇక్కడ స్టేట్మెంట్ 308 అన్నాం. సో కానీ 12th teethకి అయితే 0.308 ఇచ్చాడు అంతేనా? ఇప్పుడు ఏం చేయాలంటే నువ్వు వాడు ఏం ఇచ్చాడంటే వై ఇంక్లూడ్స్ కాస్ ఆల్ఫా టామ్ అంట కదా. ఇన్ కేస్ నీకు ఈ టేబుల్స్ వాళ్ళు ఏం టేబుల్ ప్రొవైడ్ చేస్తున్నారో నాకు తెలియదు. టేబుల్ కనుక ఇస్తే ఈ టేబుల్ కూడా ఇస్తే డైరెక్ట్గా టేబుల్ ఈ డేటా బుక్ కాకుండా నీకు సపరేట్గా సప్లిమెంట్ కింద ఇస్తున్నారని చెప్పే కదా. గేర్స్ వరకు లూయిస్ ఈక్వేషన్ డేటా ఏమి లేదు కాబట్టి దీంట్లో అది ఇస్తారని చెప్పే కదా. ఈ టేబుల్ కూడా వచ్చింది అనుకోండి మీకు దాంట్లో ఈ టేబుల్ వాల్యూ డైరెక్ట్గా ఇలా తీసుకోండి. 0.308 for 18th teeth అని తీసుకోండి. అది లేదు. ఒకసారి ఏం చేస్తారంటే ప్రాబ్లంలోనే వై వాల్యూకి వాడు ఫార్ములా ఇస్తాడు. సంథింగ్ లైక్ వై ఈజ్ ఈక్వల్ టు 0.518 మైనస్ ఇయర్ సమ్ వాల్యూ ఏదో నాకు కరెక్ట్గా జస్ట్ చెప్తున్నా అంతే. ఓకే, ఈ ఫార్మాట్లో 0.33/z/t ఎట్లయితే ఫార్ములా ఇస్తున్నాడు. y is equal to 0.518 minus 0.33/z number of teeth. సో ఇలా ఇచ్చినప్పుడు ఏం చేస్తామంటే యూ కెన్ యూజ్ దిస్ ఫార్ములా టు క్యాలిక్యులేట్ y. వాడు ఈ ఫార్ములా ఇవ్వకుండా ఈ డేటా ఇవ్వకపోతే అప్పుడు యూ హావ్ టు యూజ్ ఫ్రమ్ ద డేటా బుక్. సో ఇప్పుడు ఈ డేటా బుక్లో ఉన్న ఆ టేబుల్స్ ఇస్తే డైరెక్ట్గా పిక్ చేయొచ్చు. అట్లా కాదు, ఆ టేబుల్స్ లేవు మీకు ఇచ్చిందనంటే ఈ టేబుల్ నుంచి నీకు పిక్ చేయాలంటే ఏం చేయాలంటే ఇక్కడ ఉన్న వాల్యూని నువ్వు కాస్ ఆల్ఫాతో మల్టిప్లై చేయాలి. అడేం చెప్పాడు, వై ఇంక్లూడ్స్ కాస్ ఆల్ఫా టామ్ ఆల్సో అండ్ కదా. సో వాడు ఇచ్చిన వాల్యూ మనకి 0.377, వై వాల్యూ వాడు ఇచ్చింది ఏంటంటే 0.377. దీంట్లో కాస్ ఆల్ఫా టామ్ కూడా ఉందన్నాడు. అది తీసేయాలంటే ఏంటంటే జస్ట్ యూ మల్టిప్లై దిస్ వన్ బై కాస్ ఆల్ఫా. సో ఇన్ దిస్ కేస్ ఇట్ ఈస్ cos 20 degrees. If you take this, then you see what is the value you are going to get. You take that value as your Lewis form factor. Maybe exactly 0.308 రాకపోవచ్చు, ఏ వాల్యూ వస్తే ఆ వాల్యూ తీసుకొని ప్రాబ్లమ్ సాల్వ్ చేయండి. అర్థమైంది? ఇక్కడ ఇది ఒకటి క్రూషియల్ పాయింట్. ఎందుకంటే ఈ డేటా బుక్లో ఉంది, డేటా వేరు, మీకు ఉన్న డేటా బుక్లో వేరు, మనం ఫాలో అవుతుంది వేరు. ఇక్కడ ఈ టేబుల్ కనుక మీకు కనుక ఇస్తే ఎగ్జామ్లో, దెన్ యూజ్ దిస్. సో దెన్ అదర్వైజ్ వాట్ యూ హ్యావ్ టు డూ ఇస్ యూ హ్యావ్ టు యూజ్ దిస్ పర్టికులర్ టేబుల్. 28.13 ఏదో చెప్పారు, ఆ టేబుల్ నుంచి వాల్యూ తీసుకొని ఆ వాల్యూని మీరు కాస్ ఆల్ఫాతో మల్టిప్లై చేస్తే ఏదైతే వాల్యూ వచ్చిందో ఆ వాల్యూని పైకి తీసుకోండి. సో ఇప్పుడు ఎంత వస్తుంది, వై వాల్యూ కాస్ ఆల్ఫాతో మల్టిప్లై చేస్తే ఆల్ఫా 20 degrees అని ఇచ్చాడు మనకి ప్రజలాంగ్లు. So cos 20 degrees multiplied by 0.377, which comes out as 0.354 and awesome. So you take that value as a y and you proceed further. So నేను ఏం చేశానంటే ఈ ప్రాబ్లంలో జస్ట్ I assume that I have taken this value from the table. So I think I have shown you table. Okay, I'll let you show that again. So you have a table something like this. ఇంతకుముందు క్లాస్ ఎప్పుడైనా చూపించాను నేను అది మీకు, లూయిస్ ఫామ్ ఫ్యాక్టర్ వాల్యూస్. Maybe that is missed, the slide is missed. I think later I deleted that one. Anyway, so from the table you can pick that value. Okay, so now we decided number of teeth, and based on that we take in the form factor also, Lewis form factor also. So this is also fixed. Then what is the next step? You have to calculate the effective load. For that you need to calculate CS. CS is going to be starting torque divided by rated torque, which is nothing but 1.5. He has already given in the problem. So now to calculate the effective load based on the velocity factor, you should know what is CS and CV. These two, CS is known, CV is unknown. So to calculate this CV, you should know what is V, because your CV formula, even these formulas are also not there in your data book. Maybe in the supplement they will provide. So 3 plus V if the velocity is less than 10 meters per second. So you require this V value, but even that V value is also not given in the problem, because what is the formula for V? V is nothing but pi into diameter of the pinion, picture diameter of the pinion, and speed of the pinion divided by 60,000. So therefore you get V in meters per second. So we don't know what is the diameter of the pinion. So we know only the number of teeth here. You won't get the diameter. Number of teeth multiplied by module is going to be the diameter of the pinion. Here we don't know what is M value. We have to estimate that. So V is also unknown to you. So then what we'll do is, as the initial trial, we'll assume some velocity for V. So here he has taken it as 5 meters per second. So then with this 5 meters per second, CS can be calculated now. CV. CV is going to be 3 by 3 plus V, because it is less than 10 meters per second. Your formula for CV is 3 by 3 plus V. So this comes out as 3 by 8. So now you are in a position to calculate the effective load. Your P effective load is nothing but CS into PT divided by CV. So you can calculate that now, provided if you know the PT value. So then here one more thing is, we assume that B by M is also constant, which is taken as 10. So even this is also not given. This is the trial and error approach only. See, B by M is taken as 10. So So generally they will take it as 10. So if you want to take 8, you can take it as 8 also, no issue. Then this is the formula for calculation of the module. So in this equation, we know everything. Power is given, CS is calculated, FS is given, ZP number of teeth on pinion known, MP number speed of the pinion is known, CV is calculated, B by M is assumed, SUT is given, Y is identified. So now substitute all those data into this, we'll get the module as 4.16 mm. So now we want to, like I said, if it is 4.16, so from the table 25.2, you have to take the preferred value. That is next, you need to round it up to the next preferred value, which is 4. After 4, he has given 5 also. So then we'll take it as module as 5 mm. So once you selected the module as a 5 mm, the preference value for module is 5 mm. That's what he has given in table. Now once you know the module, you can identify the diameters of both pinion and gear also. So if module is 5, diameter of the picture diameter of the pinion is nothing but module into number of teeth on the pinion, which comes out as 90 mm. Similarly for gear it is 5 into 72, which comes out as 360 mm. So with these dimensions, of course B is 10 mm. We assume that B by M is 10, so we will get B. So now we got all the dimensions for the gear tooth or gear itself. Once you identify these dimensions, see here it is a trial one. Why we said it is a trial one is, if you take module as 5 mm, whether it is satisfying your beam strength equation or not, you need to check that also. So I think already it is now 10 o'clock, 11 o'clock. I'll stop at this point. We'll continue this in the next class. Okay? If you have any doubt, then you can ask. Still 2 more minutes of time is there. If you have any doubt, you can ask it. So I can clarify about that also. If everything is clear, respond to the attendance sheet and you can leave the class. We'll finish this in the next class. So in next class also we'll take one or two problems on beam strength and wear strength, and then we'll close this spur gears.
సార్ అటెండెన్స్ షీట్ పెట్టలేదు కదా సార్.
అటెండెన్స్ షీట్ పెట్టలేదమ్మా.